Okay, so now we start with reflecting telescopes, which use a main mirror. And they use the principle of reflection, which is a lot easier to understand than refraction because, you know, we look at mirrors all the time. So some of us more than others, I guess. But reflection is simply very simple. When light hits a surface that reflects, it just and bounces off and travels on its way. And so a mirror is used at the bottom of a reflecting telescope, and it'll be curved to allow, again, the rays to come in and focus at a single point, and that is where the image is going to be located. So reflecting telescopes use mirrors. A basic reflecting telescope might look something like this. Notice that the mirror is at the bottom. It's a different sort of orientation or organization than a refracting telescope. This is where the image is going to be focused, and so you'll read about in your book that different types of telescopes can use different methods to get that image out to where it can be observed, with using multiple mirrors or putting an observer right there. There's different ways of doing it, and different orientations have different advantages that you can read about. So, now that we know the two basic types of optical telescopes, what are the two most important things about them? Well, as I said before, the light gathering power, the ability to collect as much light as possible, is very important. And another thing that we're going to talk about is the angular resolution, or the resolving power, which basically means how sharp and how crisp can my images be. So the main part of a telescope, whether it be a lens or a mirror, is going to determine how much light it can collect. And as you see in these two pictures here, you can see obviously why bigger is better. The larger lens here is able to collect more light, therefore we're going to be able to see more with it. What we need to say to be in more detail is that light gathering power of that telescope is directly related to the area of the main lens or mirror. So the cross-sectional area of the lens or mirror is what is going to determine the light gathering power. So however much that area increases, that's how much the light gathering power is going to increase. So, for instance, if I have two telescopes, telescope A has a diameter of 3 meters, while telescope B has a diameter of 9 meters. We want to answer the question, which has better light gathering power? Hopefully you're able to narrow these answers down pretty quickly by recognizing that because telescope B has a larger diameter, that's definitely going to be bigger. The question is, how much bigger? Now think about the fact that it's related to the area, and these lenses or mirrors are going to be circles, and how am I going to find the area? You can use the expression pi r squared, and so the diameter, of course, is just twice the radius, so we could say it's pi d squared over 4. It's the same thing. But notice that the area is going to be related to the diameter squared. So telescope B is 3 times larger in diameter, but we would square that 3 to say how much larger the area is. So 3 squared is 9. So the answer is that telescope B has 9 times the light gathering power of telescope A. Now, angular resolution. In this picture here, you're seeing two different types of angular resolution. In the left-hand picture, you just see that we're looking at something that looks kind of oval-like, a blob. It's not really clear. Maybe it's two things that are really close together, but it's not clear here. Where in the right-hand picture, we actually see that we are looking at two distinct objects that are relatively close together. So, in the left-hand picture compared to the right-hand picture, the left-hand picture has a poorer angular resolution. The better angular resolution allows us to see objects that are very close in the sky as two distinct objects. And if they are very close in the sky but we can still see them, we say that we are able to resolve them as separate objects. And we say that that allows us to have a certain amount of angular resolution. So, as I said, the angular resolution is the ability of a telescope to form distinct, separate images of objects that are very close together in the sky. Close together, remember, we measure the closeness of something in the sky by an angle. So we actually want our angular resolution to be small because we want our objects to have a very small angular separation and still be able to be seen as separate objects. So that sometimes is confusing, that in terms of light gathering power, we want it to be big. Angular resolution, it's actually desirable that the angular resolution is small. Small is good for angular resolution. Try to remember that. And in terms of how we express angular resolution, it will be expressed as an angle. It'll be the smallest angle that can separate objects that we can still see them as separate. Now, the expression for angular resolution, like how do we determine what determines angular resolution? There's two things that come into play for angular resolution. And that is the wavelength of the light that we're looking at and the diameter of our telescope. The angular resolution is directly related to the wavelength. So that means that the longer the wavelength, or the bigger the wavelength, the bigger the angular resolution. But remember, that's not a good thing. Big angular resolution is not what we desire. However, angular resolution is inversely related to the diameter. And so that helps explain for a telescope why bigger is better, because a larger diameter telescope will give us smaller angular resolution. The reason that we have issues with resolution is that the resolution of an image is limited by the diffraction and interference of light. And this picture is actually showing both. The two ripples in the pond are interfering or adding up together. That's interference. And the fact that the ripples were caused probably by some disturbance right here and right here, which actually spread out, that's diffraction. Let's take a look at that a little bit more closely. The diffraction of waves is when light goes through an opening and it spreads out after it goes through the opening. So in this picture we're not seeing much diffraction, but in this picture we are. And so the comparison between the opening and the wavelength determines whether or not there's going to be diffraction. When the wavelength is equal to or much larger than the opening, we get a lot of diffraction. And so that helps you understand why longer wavelengths they diffract more and they actually work against our angular resolution. The interference of waves is how waves interact when they come together at the same location at the same time. So remember, light is like a wave. So these two waves are adding together. Notice they're doing the same thing at the same time. They both have high peaks at the same time. They both have low peaks at the same time. And interference simply says that if these two waves came together at the same location, the wave that you would get would be simply found by adding them together. These two waves, because they're completely in sync with each other, are interfering constructively. While this second picture shows you something completely opposite, where these two waves are doing exactly opposite things at the same time, and therefore, because this has a trough when this has a peak, when you add them together you get no disturbance or no wave, and this is called destructive interference. And then somewhere in between would be where they're not completely lined up, not completely adding up or subtracting. It's just sort of just general interference. So when light comes into a telescope, because of the opening, there can be some diffraction and also some interference of the different light waves, and that's really what affects it. The long wavelengths are going to make the resolution larger, while the large opening helps to offset that, because the large opening will help our diffraction, our resolution. The diffraction limit is what is the best possible resolution you can hope for, which is found by an equation that's 2.5 times 10 to the fifth wavelength over the diameter, and that would be measured in arc seconds, which remember is a fraction of a degree. You're not really going to be working too much with this calculation. What I really want you to remember about resolution is that longer wavelength gives larger resolution, which is bad, but larger diameter telescopes give you smaller resolution, which is good. So I think I made a mistake here by highlighting the wrong slide, but let's just look at it anyway. Telescope A has a diameter of 2 meters and telescope B has a diameter of 4 meters. Which telescope has better angular resolution? Now, at first we might get a little confused because we know the resolution should be small, but remember, the bigger is better is always going to apply to telescopes. So telescope B is definitely going to be bigger. And the reason is because the angular resolution is equal to 1 over the diameter, so 1 over a bigger number actually gives you smaller angular resolution, which is what we want. So 4 is the bigger one. The relationship is just 1 over the diameter, so this is 2 times bigger, which means that we only have 2 times better resolution. So you have to keep in mind those two relationships for resolution for two telescopes and light gathering power. The rules, bigger is better, is always the same, but we have to remember for light gathering power, it's related to the diameter squared, but for resolution, it's just related to the diameter. Now, one of the downsides to resolution is no matter how good our telescope is, the atmosphere affects the resolution of our telescope, because when the light rays come into our atmosphere, they bounce around off the air molecules, and this actually disturbs our resolution and makes it a little bit larger than we wanted it to be. Typically, the amount is going to be about 1 arc second, and we call this the seeing caused by the atmosphere. So this is going to be added to the resolution of our telescope no matter what. But that is actually why we like to build telescopes up on the top of the mountains, because if you put it up on top of the mountains, you're not dealing with as much atmosphere. And this is where we're going to finish this part of the lecture, and I'll have a third part to finish up telescopes that you can watch.